Good afternoon, everybody. My name is Ranjita, and I'm a PhD student from Georgia Tech, advised by Dr. Brendan Saltafamaggio. I'm presenting our paper, TARDIS, Rolling Back the Clock on CMS Targeting Cyber Attacks. Hosting websites have become very easy. So easy that my grandma in India has a website too. All of this has been made possible by the rise of content management systems. Not many people have heard of content management systems. CMSs? Anybody? But if I were to tell you WordPress or Drupal, then everybody knows what I'm talking about. That's because CMSs market themselves majorly to non-technical users. So, what is a CMS? A CMS can be thought of as an amalgam of layered software and interpreters, starting with the web server framework, the database, the HTTP server, interpreter, and a CMS layer on the very top. Most of these layers are hosted on leased or rented infrastructure in the cloud. Also, they have varied network and systems permissions. The CMS itself can be thought of as CMS core and CMS plugins. Both the core and the plugins contain code templates, and these code templates allow someone such as my grandma to drag and drop a couple of elements and build a full-fledged website with only a few clicks. A recent statistic showed that over 55% of the world's websites run on content management systems. Attackers love CMSs too. Their huge market share, combined with less technical users, make CMS-based websites a right target for attackers. In fact, our research found that these attacks are not simple script kiddie attacks. They're complex, long-lived, multi-stage attacks that attackers try all kinds of stealthy methods to ensure persistence. In collaboration with CodeGuard, one of the largest website backup service providers on the market today, we analyzed more than 300,000 websites. That's a lot of websites. Our study spanned an average of 1900 days from 2014 to 2019. And we found that 20,591 websites were compromised with long-lived multi-stage attacks. To investigate such attacks, traditional forensic techniques used fine-grained logging. Unfortunately, all of these techniques rely on the OS layer and the CMS stack. Turns out these techniques are hardly deployed in practice. That's because of the performance or space overhead associated with them. Besides, even if the website owners wanted to deploy these techniques, they have no control over the web server. That's because most of the layers on the CMS stack reside on rented infrastructure. Also, these techniques require significant instrumentation and training, which is not accessible to our non-technical website owners. So, what are the website owners doing today? The industry standard has moved to the backup and restore model of security. There are several backup service providers on the market today, such as CodeGuard, iPage, Security, DropMySite, GoDaddy, to name a few. The backup service providers maintain nightly backups of their clients' websites, and they have an integrated antivirus or an AV on the backup site. Each time the AV finds something suspicious, the website owners are alerted. This has a few limitations associated with it. First, AVs catch only well-known malware. Also, high false alarm rates associated with AVs have resulted in threat alert fatigue, where website owners end up ignoring true alerts from the AVs. When someone such as my grandma gets an alert and is posed with the question of restore or ignore, how is she supposed to decide what to do next? As we'll see later, this research actually found that for only 31% of the true positive AV alerts, the websites get restored. The rest of the true positive AV alerts are ignored and they don't get rolled back. The infection just continues. Consider a case where my grandma's website is infected. A non-technical user such as my grandma faces several challenges. The research solutions are not being applied, the industry standard is not working, and we only have the website backups in hand. So how do we recover these infected websites from the long-lived multi-stage attacks? And that's when TARDIS comes to the rescue. Not the time machine from the popular TV series Doctor Who, but a framework we developed by taking inspiration from the show. Similar to TARDIS from Doctor Who, our TARDIS is also capable of time travel. It takes the website backups as input, goes all the way back in time, and analyzes every single snapshot. It records certain metrics for all of these snapshots, correlates these metrics, and extracts what we call a compromise window, or the period of time when the nightly backup snapshots must not be trusted. Let's dive a little deeper into the design of TARDIS. TARDIS takes the website backups as input and enumerates the contents of each snapshot into spatial elements. The spatial elements are essentially files that are in each snapshot. But that leads us to a problem. Each snapshot contains tens of thousands of files on the web server that we found to be over 11,000 on average. So, we need to reduce the spatial elements to a set of spatial metrics. Basically, measurements of how these elements evolve over time. TARDIS measures these spatial metrics via spatial analysis. Due to the large volume of spatial elements, TARDIS separates spatial analysis to first identify structural metrics. The metrics that don't depend on the contents of the files, such as when they got added, modified, or deleted, the file type numbers in a given snapshot, etc. It then records the code metrics by analyzing the contents of all of the code files. Here, it considers behaviors such as code generation capability, presence of obfuscated code, to name a few. You can find a full list of structural and code metrics on our paper, and that gives us a set of complete spatial metrics. While these metrics on a single snapshot may not reveal much, their evolution over time allows you to identify a compromise. And that brings me to the key idea behind TARDIS: measuring sudden changes in between snapshots for these spatial metrics. Let me give you an example. Here's the temporal progression of one of the spatial metrics, the differential file type numbers, for a single website that was infected over and over again. The highlighted lines here show you that the infection began all the way back on 21st April 2018. Despite cleanup effort between 5th and 8th June, we see the infection reoccurring on 13th June. TARDIS applies this key idea of temporal progression to temporally correlate the previously recorded complete spatial metrics. It takes the complete spatial metrics and passes it through an n-day sliding window to extract the spatial metric evolution. It then assigns attack labels to each of the nightly snapshots. These labels include obfuscated code injection, defense evasion, escalating privileges, attack cleanup, etc. Please see our paper for the precise definitions of these attack labeling rules. This leaves us with the labeled nightly snapshots. TARDIS then proceeds to extract the compromise window from these labeled nightly snapshots. It first evaluates the differential spatial metrics for every pair of snapshots and records the sudden changes. It then feeds this to an outlier analysis algorithm, which assigns anomaly scores to each of the snapshots. TARDIS also ensures that the assigned attack labels form a logical sequence. For example, attack cleanup cannot be seen before obfuscated code injection or malware dropped. Using the verified labels and the ranked anomaly scores for each snapshot, TARDIS extracts the compromise window and produces the verified labeled snapshots. Now, armed with this information, someone such as my grandma can easily restore their infected website outside of the compromise window. So we designed TARDIS, but we wanted to evaluate how well TARDIS would perform in the real world. So we took backups of 163 websites as our ground truth dataset. Our team reverse engineered these websites by hand and found that 80 of these websites were compromised. We also ran TARDIS on these 163 websites, and TARDIS found 83 websites as compromised with 3 false positives. Our manual investigation revealed that all 3 websites contained user-developed security plugins with obfuscated code, very similar to the tactic employed by attackers. We found that these false positives were within a tolerable range and decided to deploy TARDIS in the wild to understand the attack landscape of present-day CMS-based websites. We analyzed more than 300,000 websites, and their distribution roughly matches the market share of each CMS platform. TARDIS found more than 20,000 compromised websites, and not surprisingly, the attacks also roughly match their distribution. As mentioned earlier, most of the CMS platforms contain tens of thousands of files on average. But what's more interesting is the comparison of the number of files in compromised versus benign websites. During a compromise, attackers are actually dumping tens of thousands of files on the web server. And this has led to a running joke in our lab that these attackers are causing a dumpster fire everywhere they go. To learn about the persistence of these attacks on different CMS platforms, we compared their compromise windows. This graph has been truncated to 300 days for clarity. What's not shown here is that more than 20% of the attacks on WordPress websites persist between 300 to 1694 days. That's more than 4.5 years. But on average, attacks on WordPress websites persist for about 40 days. Attacks in other CMSs such as Joomla and Pivotex persist for a little longer, around 75 to 85 days. We now compare TARDIS against the industry standard of using AVs at the backup site. Of the 300,000 websites that we analyzed, TARDIS found more than 20,000 websites were compromised. In comparison, the AV on the backup site identified compromises in only 91 websites. This is less than 1% of the total attacks identified by TARDIS. Of these 91 websites with true positive AV alerts, the website owners for only 29 websites initiated a rollback. This goes to prove that threat alert fatigue is a real problem. This is the abysmal 31% of the true AV alerts that we called out before. Furthermore, of the 29 websites that attempted rollbacks, 19 websites were reinfected, thus indicating the industry standard of backup and restore is not working. A system such as TARDIS helps significantly in mitigating this problem. Correlating TARDIS's results at a cross-website level can be used to understand the global view of attack movement. These 5 websites here belong to different unique small businesses that just happen to build their website upon WordPress. Interestingly, each of these websites exhibited the exact same attack phase evolution and persistence for the exact same duration. This information extracted by TARDIS can be leveraged to identify global attack campaigns. In another case study of a Drupal-based website, the attack was initiated via obfuscated code injection, followed by malware dropped, escalating privileges, and eventually cleaning up the attack traces. However, it was amusing to find that the attackers injected a full-fledged GUI that allowed them to control all the contents of the web server. In conclusion, we introduced TARDIS, a novel provenance inference technique that can identify compromises in CMS-based websites using only the already collected nightly backups. TARDIS uncovered more than 20,000 long-lived multi-stage attack victims. This is some of the related work that motivated the design of TARDIS. We would like to thank IEEE Computer Society and the Security and Privacy Organizing Committee for their effort to take this conference online. Your leadership in this highlights how resilient our community is. And a big thanks to CodeGuard for collaborating with us on this research. We never could have done it without them. Thank you for helping out in making the web a safer place for all of us. Last but not least, thank you everybody for making it to the end. Your 3 minutes for questions is starting now.